introduce a very important article in NIPS 2018 by people like Neil Lawrence. I like this person very much. He works in Amazon. And the article is Variational Mutual Information Distillation for Transfer Learning. Of course, transfer learning is a huge topic, and very important for the scalability of machine learning in future. But when people talk about distillation, it is a category of knowledge distillation. It is because you have a very complex deep learning model with billions of parameters, and you want to just simplify that model and make it simple and with just a few parameters, maybe thousands instead of billion parameters. So you see that it is a very important goal because you want to reduce the complexity. So it's something like you feel it's like the opposite of overfitting, because you want to reduce those complicated dynamics and those, because most of them are, you don't need most of these parameters. So in this beautiful article, we want to maximize mutual information between student and a teacher. Because we have to maximize the amount of relevant knowledge being transferred from a teacher network. Teacher network is usually that complicated and very big, deep neural net with billions of parameters. And the student network is very simple model. Usually it's very simple. And the mutual information is intractable for doing this. And that's why we use tractable, analytic, variational lower bound. And in this article, they have implemented that using Gaussian observation model. So the method is like this. We have a source, like any transfer learning method. We have a source, and here we call it teacher neural network. So we have K layers. Let's say K is equal to 4. We have only 4 layers. And then we have a target, just like any transfer learning. We have a target with loss L of S. And we call it student neural network. The number of neurons in each layer could be reduced significantly, but here the number of layers, you keep the number of layers. So if it is K equal to 4, here K is equal to 4 as well. So K is fixed. And because you have fixed for any student and a teacher, and a student and a teacher, we have a pair. So we have teacher at layer K and student at layer K from 1 to 4, for example, number of layers. It's a function of input X. So T of K is just this, and S of K is just number of input. It's a function of input. So the mutual information between teacher and student is entropy of T minus conditional entropy of T conditioned on S. So this is a conditional entropy. And this is equal to minus expectation. You draw from P of teacher. You draw log of P of T plus expectation. Now it's a conditional distribution. So T and S drawn from this joint distribution of log of P of T condition and S. So P, T, and S is a result of aggregation over the layers with input X, but it is sampled from empirical distribution P of X. This is the empirical. And what is our loss? We want to minimize with respect to the student parameters. Don't forget that it is student parameter. So we say it is a loss for the target. Target is student neural networks. For the target, this is as usual, because any neural networks has a loss. But simultaneously, you want to also reduce this as well. Lambda k, which is a hyperparameter, mutual information between case layer of teacher and the case layer of student. So this term encourages high mutual information with the teacher network. So you see how easy it is. And of course, the minimization is hard and intractable, but we use a variational lower bound for each I of T and S. And Q of T condition on S. So as usual, this approximates PT condition on S. So just computing the mutual information would lead to H of T minus conditional entropy. H of T, this is very important because instead of H of T condition at S, we can write expectation of T and S drawn from T and S, log of PT condition on S. So adding and subtracting, the usual trick, in order to observe a beautiful KL divergence. So our motivation is just to show this beautiful KL divergence between and QT condition and S. Why do we love it? Because it is positive. So this one plus expectation of TNS drawn from PTNS log of QT condition on S. So because that is positive element and this is our goal. So what we can do is because it's positive, so it's greater than H of t, which is constant, we can remove it, plus expectation of log of QT condition on S. So we just remove that positive element and what we are left with is this. So L is jointly minimized over the parameters of student network and the auxiliary distribution K. Q. So lambda K, expectation of teacher, case layer, student, case layer, TK and SK. Expectation of log of Q, case layer of T conditioned on case layer of S. And I highly encourage you to read this article. It is called the IM algorithm. It means information maximization. The IM algorithm, a variational approach to approach to information maximization. And finally, I should say your implementation is, there are lots of ways you can approximate and to represent your distribution. One easy way is just this. Log of sigma d plus minus mu d of s squared over 2 sigma d squared plus constant. And this one is this entry of vector t, your teacher given student. And I think that's enough for this weekend. Have a great weekend. Cheers. Bye-bye.